Good evening, everyone. It's my pleasure to be here as a part of this international webinar series on advanced characterization techniques organized by UANL ECS Student Chapter. Today, I'll be discussing about a powerful as well as widely used characterization technique in material science and technology, that is a high-resolution X-ray diffraction technique, or HRXRD. HRXRD plays a very critical role in analyzing structural properties of thin films with a very high precision. Whether you are studying epitaxial thin films, polycrystalline thin films, semiconductor wafers, or even multi-layered structures, it can provide a great insight that are essential for both research as well as industry applications. With that short note, let us start exploring some of the basic theory and applications of HRXRD. This is the outline of my talk. First of all, we will give a brief introduction to X-ray diffraction and normal powder diffraction method. Then we will move on to HRXRD application, some of the HRXRD application. First of all, we will be discussing about glancing angle XRD theory and applications of glancing angle. Then we will move on to pole figure analysis and reciprocal space mapping. We all know that diffraction occurs when light is scattered by a periodic array with a long range order. It produces constructive as well as destructive interferences. The necessary and sufficient or essential condition for light to be diffracted by a periodic array is that the width of the periodic array should be of the order of the wavelength that we are using. For example, we know that atoms in a crystal are arranged periodically with the interplanar spacing of the order of few nanometers. Then if you have to use crystals for diffracting light, the wavelength should be of the order of few nanometers. And it was William Röntgen in 1895 discovered X-rays while he was experimenting with the cathode rays. And in 1912, Max von Laue conducted first diffraction experiment while by passing X-rays through a crystal. He observed distinct diffraction patterns. He observed, and that proves there is an internal periodic structure for crystals, and that X-rays could be used to study the internal periodic structure of crystals. And it was in 1913, W.H. Bragg and his son William Lawrence Bragg put forward Bragg's law. It was a simple mathematical model which relate the angle of diffraction with the interplanar spacing as well as with the wavelength of X-rays used. And the equation is given by 2d sine theta is equal to lambda. When lambda is kept constant, we can directly relate the interplanar spacing with the angle of diffraction. Thus, from the angle of diffraction, we can directly determine the interplanar spacing, or from that we can determine the structure of the materials. And now it plays a very critical role. This equation plays very important role in interpreting XRD as well as determining crystal structures. When we talk about evolution of X-rays, first of all, powder diffraction method was developed for studying polycrystalline thin films, which consist of many crystallites that are randomly oriented. And with the advent of technology as well as instrumentation, it led to the development of high resolution XRD, which plays a very critical role in analyzing epitaxial thin films, polycrystalline thin films, surface layers, etc. Today, XRD plays a very important role in not only in crystallography but also in chemistry, material science, nanotechnology, biosciences, allowing scientists to develop design new materials and to study the properties of the material at an atomic level. Now we move on to the essential part of a diffractometer. First one is X-ray source, which generate X-rays. Then beam conditioning system, which particularly shape and purify X-ray beams, which consist of filters, slits, and monochromators. Then sample holder, which holds a sample as well as it allows some rotation of the samples. Then goniometer, which controls the angular movements of the sample along omega direction, 2 theta direction, and other movements also. Then detector, which captures diffracted X-rays. Then a data acquisition system, which converts the detector signal into digital format, and the computer software, which operates the instrument, collects the data, and perform the analysis. Now we are move on to discuss some basic principle of powder X-ray diffraction or normal X-ray diffraction. It uses Bragg-Brandonau geometry, or it commonly known as theta to theta geometry. Here, the incident angle, the configuration of the Bragg-Brandonau geometry or theta to theta configuration is shown in the figure. It should be noted that it uses a focusing configuration. That means X-ray tube and the detector converge on a focal point that you can see here. X-ray source and the detector are on the same focal circle, converge on the same focal circle. Here, the incident angle is defined between the X-ray source and the sample, and 2 theta is defined as the difference between incident angle and the diffracted angle. Here, the diffracted angle moves twice as that of the incident angle. It should be noted, it's very important. The diffracted angle moves twice as that of the incident angle. Therefore, it is called a coupled scan. That means a detector and the source are coupled here. The movement is coupled. In this geometry, the sample rotates. If the sample rotates in theta degree per minute, then the detector rotates 2 theta degree per minute. An animation of Bragg-Brandonau geometry is shown here. Also, here the scattering vector. This is a scattering vector, which is the bisection of incident beam and scattering diffracted beam. This scattering vector will always be normal to the sample surface. That is, in the Bragg-Brandonau geometry, the scattering vector will always be normal to the sample surface. This is very important. That's why it is called a symmetric scan. There are several advantages for this coupled symmetry scan, as well as there are several disadvantages for this also. Since the scattering vector is normal to this sample surface, we can only detect those planes which are normal, which are grown parallel to the sample surface. This is one of the major disadvantage of Bragg-Brandonau geometry or normal theta to theta geometry. We can only detect only those planes which are grown parallel to the sample surface. So what are the information that we can get from this diffraction pattern? A typical diffraction pattern in a theta to theta geometry is shown in the figure. This relative intensity versus 2 theta graph. From this, what are the information that we can get? From the peak position, we can directly determine the angle of diffraction, or the interplanar spacing can be calculated using Bragg equation. The peak position from the interplanar spacing, we can calculate a unit cell space groups. Also, the peak position may change with the composition and stress within the film. Second thing we have to note is the peak intensity. The peak intensity is given by the preferred orientation in the sample. Is directly proportional to the preferred orientations in the sample. That is, how many number of planes that are parallelly oriented within the sample. If the number of planes parallelly oriented is very large, the peak intensity of that particular peak will be large. And another thing we should note is the peak shape. It refers to the peak shape refers to the quality of a single crystalline thin film. That means it can give it will give a measure of defects or stress in the thin film. Also, we can calculate the crystalline size from the peak shape, from the full width of maximum of the peak shape using Scherer formula. Peak shape also determines the symmetry of the peaks, also determines strain within the thin films. We can quantify the strain by the symmetry, from the symmetry of full width of half maximum of the peaks. So what are the key limitations of theta to theta geometry? As we have discussed, uh, here in the case of Bragg-Brandner geometry, the scattering vector will always be normal to the sample surface, or we can detect only those planes which are normal to the sample surface. That means an example of an example XRD graph is shown in the figure. Here we can see a 100 oriented plane at an angle of about 21 degree. That means 100 planes satisfies the Bragg's angle at this particular angle, Bragg's equation at this particular angle, and the surface and the planes are parallel to the sample. Here there are 110 and 111 peak also there, which may satisfies the Bragg equation at an angle of 29 or about 36, but it may not be visible even if they're present. Since these peaks, that is 110 peaks and 111 peaks, may be tilted to the sample surface. If the surface is like this, the 110 peak and 111 peaks are tilted to the sample surface. They may not be normal to the sample surface. In those cases, these planes will not be visible in the Bragg-Brandner geometry, in the X-ray diffraction spectra taken using theta to theta geometry or Bragg-Brandner geometry. And here the 200 peaks, which is parallel to 100 peak, can be seen. The interplanar spacing of 200 peak is about half of that of 100, and so we can see the 200 peak at an angle twice that of the 100 peak, that is about 42 here. So what we have to do to observe these 110 and 111 planes, that is those planes which are tilted to the sample surface. In order to observe these planes, we have to tilt the sample and then take XRD diffraction. This type of scan is called asymmetric scans, in which the scattering vector, if you note in this figure, the scattering vector is now not parallel to the sample surface, but perpendicular to the sample surface, but now it is perpendicular to the planes since we tilted the samples. So the key limitation of a theta to theta geometry or Bragg-Brandner geometry is that it can only detect those planes which are parallel to the sample surface, and other orientation, that is tilted orientation, do not produce diffraction peaks. They cannot detect tilted or misoriented planes. This limits the ability of a Bragg-Brandner geometry to study off-axis orientation or strained thin films, tilted thin films. So how can we overcome this limitation? One method is to use, as we have discussed, to use asymmetric scans or a reciprocal space mapping that we will discuss in the later slides, or employ grazing incidence or rocking curve analysis. These are the different techniques that we can use to detect the tilted orientations. They can only be done using an HRXRD equipment. Here is a comparison of ordinary XRD versus high resolution XRD. Some features. The resolution of ordinary XRD is only moderate of about 0.1 to 0.01 degree, whereas in the case of HRXRD, it is around 0.001 or higher. In the case of instrumental setup, normal XRD needs a simple setup here. Simple goniometer and broad beam optics will do the work. Whereas in the case of HRXRD, we need high precision goniometers, monochromators, collimators to do high resolution XRD. Ordinary XRD can be used to study bulk materials, powders, polycrystals, whereas HRXRD, in addition to bulk materials, we can do epitaxial thin films, multi-layered structures, superlattices, that we can study with the HRXRD. In the case of ordinary XRD, we can only do a normal theta to theta scans, whereas in the case of HRXRD, we can do multiple scans like omega to theta scan, rocking curve scan, reciprocal space mapping, pole figure analysis, X-ray reflectivity, glancing angle XRD. These all features are there in HRXRD. So, what are the features that we are going to discuss in today's presentation? We will discuss, first we will discuss a glancing incidence XRD, which is used to phase analysis study of very thin films and surface sensitive thin films. Then we will move on to pole figure measurement. It is used to determine the orientation distribution in the crystallites and map them onto a three-dimensional space. And if the time permits, we will discuss a reciprocal space mapping also, where we can study strain, relaxation, or defects or tilt in the thin films. Before moving on to in details of HRXRD, we should know different angles that we are using in HRXRD measurements, how these angles are defined. Here, two pictures, two perspective of X-ray diffraction scheme is given. In this case, a film is placed vertically, and here is the source, X-ray source, and here is a detector. In this case, theta is defined as the theta or omega. There is a difference between theta and omega that we will discuss in the later sessions. Theta or omega is defined as the angle between sample and the X-ray source. 2 theta we have discussed. It is the angle between incident beam and the diffracted beam. The other two angles we should know is, one is psi angle or tilt angle. It is called a tilt angle. It is the angle between scattering vector and the surface normal. Scattering vector is the bisection of incident beam and diffracted beam. So psi, the tilt angle, is the angle between the scattering vector and the surface normal, and the another angle is phi angle. It is also called azimuth angle. It is in this direction. It is used in the rotation of samples in the pole figure analysis. Now we move on to discuss glancing incidence theory of glancing incidence XRD or grazing incidence XRD, or it is commonly known as a GID. In case of X-ray radiations have large penetration depth into the material of the order of 10 to 100 micrometers. So when we use these X-rays to analyze thin films in our normal XRD, normal Bragg-Brentano geometry, these X-ray will penetrate into the substrate. So major features that we will be seeing is from the substrate itself. So we will be missing out minute features of the sample. This happens especially when we use deposit thin film on a single crystalline substrate. The peak from the single crystalline substrate will be very large, so we'll miss out minute features of our film. So in case of normal XRD, the major contribution is from the diffraction from the substrates itself. So up to some extent, we can say that XRD technique is not surface sensitive. And GID or glancing incidence XRD is designed to overcome this difficulty. Here in GID, glancing incidence XRD, the angle of incidence will be very small, of the order of about 0.5 to 5 degree. So the penetration depth will be very small in glancing incidence XRD. This allows several possibilities like phase analysis of very thin films, of few nanometers could be done using GID. Also, surface sensitivity can be down to up to few nanometers. And even we can do depth profiling in multi-layered structures by changing the angle of incidence. We can do depth profiling. Here, X-ray, the figure shows X-ray penetration depth as a function of angle of incidence in the low angle regime as well as in the high angle regime. If you see in the first figure, it is a penetration depth is taken along the y-axis and angle of incidence is taken along the x-axis. In the high angle regime, the penetration depth is very large. These are for materials like carbon, lead, and silicon. For all these cases, the penetration depth is very large when the angle of incidence is very large. That means it is of the order of 10 to 100 micrometers in the large angle regime. Whereas in the case of low angle regime, the penetration depth reduced to about a few nanometers. That means when the angle of incidence of X-ray is very small, of the order of from 0.1 to 0.5, in this region, the X-ray maybe we can confine the X-rays within the film itself, not going to the substrate. Thereby increase we can decrease the penetration depth and increase the path length that X-ray traveling through the material. By increasing the path length, we can increase the intensity of the peaks. There will be large enhancement of in the intensity of the peaks from the sample, since the path length has been increased. So, how does a GID works? Can we configure our normal powder XRD machine to take GID? Or how can we configure our powder diffractometer? Can we configure our powder diffractometer to take a glancing incidence XRD? The answer is not directly. In the case of normal XRD, as you can see, the 2 theta detector angle moves twice the speed of the incident angle, or as we have discussed, it's a coupled scan. It's a coupled scan. In this case, the scattering vector will be normal to the sample surface. Here, the samples, in this case, the scattering vector in this direction is always will be normal to the sample surface. And as we have discussed in the previous slides, we can only detect planes which are normal to the, which are grown parallel to the sample surface in this normal XRD. Whereas in the case of GIXRD, the incidence angle of incidence is very shallow, of the order of 0.5 to 5 degree. And here the detector angle only moves. Here the source is at a fixed angle. Here the X-ray source or angle of incidence is fixed at a very low angle, and the detector itself only moves here. That means it's a decoupled scan. In the case of normal XRD, it was a coupled symmetric scan, whereas for doing GID scans, we need the detector and source to be decoupled so that they can move independently. Here, in this case, X-ray source is fixed and detector only moves in the 2 theta direction. The important advantage of this particular configuration is that the scattering vector is now not perpendicular to the sample surface. It changes. The direction of scattering vector changes with respect to the detector angle. That means here in this configuration, in this GID configuration, we can also detect not only the planes which are normal to the sample surface, but also those planes which are tilted to the sample surface. The main disadvantage of normal XRD was that it is a coupled scan and it was symmetric scan. We cannot detect those planes which are tilted. Whereas in the case of GID, since it's a decoupled and asymmetric scan, it can detect all those planes which are parallel to the sample surface and tilted to the sample surface. This is the instrumentation we require to do the glancing incidence XRD. We need parallel beam optics to maintain low divergence. Need specialized monochromators to reduce the spectral noise, and even need two-dimensional detectors. Sometimes we need two-dimensional detectors. I'm not going to discuss this instrumentation part now. Here is a comparison of X-ray diffraction pattern from normal X-ray diffraction and a glancing incidence from a sample, a polycrystalline silicon sample of about 100 nanometer thickness deposited on silicon substrate. The red spectrum shows the XRD spectrum from conventional theta to theta geometry, whereas the blue spectrum is from the glancing angle XRD. We can see that from this itself, we can see that in the case of normal XRD, the peak intensity, the intensity of the peak from the substrate is very large. And the peak intensity, the red color spectrum, the peak intensity from the sample is very low. Whereas in the case of glancing incidence, we cannot see any substrate peak from here. And also the intensity of the peak has been increased in the case of glancing incidence XRD. Here is yet another example which compare the normal XRD scan with the GIXRD for a rutile titanium dioxide deposited on ferrite substrate with a very small titanium buffer layer. In this case, in the case of normal XRD, we could see that the substrate peak intensity is very high from the substrate. Also, the sample intensity is very low. Whereas in the case of GIXRD, we could see highly resolved and high intense peak from the sample itself. We could not see any peak from the substrate. That means in the case of GIXRD, since the angle of incidence is very small, the X-rays are confined within the sample itself, not going to the substrate. Thereby, we can observe highly resolved peak from the sample. Here is a comparison of advantages and disadvantages of grazing incidence versus a Bragg-Brentano configuration. In the case of grazing incidence XRD, we could detect grains in various orientation, including tilted to the sample surface, whereas in the case of normal XRD, we could only detect only those grains which are parallel to the sample surface. In the case of grazing incidence, since the angle of incidence is constant, therefore the depth probed will be constant during the entire measurement. Depth of the sample, depth into which the X-ray probe into the sample will be constant or will be fixed throughout the analysis, whereas in the case of conventional XRD, sample probed length may vary during the analysis since angle of incidence changes. In the case of glazing incidence, it has high sensitivity to ultra thin films. It avoids artifacts from the substrates, can be used for depth profiling at a different angle of incidence, whereas in the case of conventional theta to theta geometry, we could not do any of this. Since we are using a parallel beam geometry in the case of grazing incidence, it is insensitive to the sample displacement errors. Whereas in the case of normal XRD, it is highly sensitive to sample displacement error. That is how we fix a sample. One of the disadvantage of grazing incidence XRD is that it has slightly lower 2 theta resolution than normal XRD. Since normal XRD uses a focusing configuration. That is, as we have discussed, the detector as well as the X-ray source converge on a focal circle. It has a good 2 theta resolution. Whereas in the case of glancing incidence, since we are using a shallow angle of incidence, the footprint, X-ray footprint on the sample will be elongated along the surface. This contribute to the 2 theta widening of the sample or peak widening of the sample. So it has slightly lower 2 theta resolution than that of the normal XRD. Now we move on to our second part of our presentation, how to characterize epitaxial thin films using HRXRD. So what is an epitaxial thin film? Yes, epitaxial thin film is a single crystalline film or highly oriented film that has been deposited or grown over a single crystalline substrate. They can be classified into two, that is homoepitaxial layer, where the film and the substrate are of the same material. That means the lattice mismatch between the film and the substrate is very low, or in that case, the film can be grown, film can be strained with strained to match the lattice constant of the substrate. Whereas in the case of heteropitaxial thin films, the thin film material and the substrate material are different. In this case, if the lattice mismatch between the film and the substrate is very large, the film will grow largely relaxed manner. So this preferred orientation in an epitaxial, how can we determine if there is an epitaxial growth in our thin film? It can be easily determined from a normal theta to theta geometry by observing if there is any pronounced enhancement in the peaks in the theta for a particular plane. If there is by observing if there is a pronounced enhancement in the intensity, there could be a preferred orientation in our sample in that particular direction. The preferred orientation is usually quantified by the term texture. So what is meant by a texture? Texture is a measure of crystallographic orientation in a sample. For example, if we consider an ideal polycrystalline thin film, which has a large number of randomly oriented crystallites in all the directions, they have zero texture or low value of texture, where normally in normal materials, grains or crystallites will prefer to be oriented in certain particular direction. That means there will be some preferred orientation in our sample. And the degree of preferred orientation depends on how much percentage of the crystallites having that preferred orientation. This texture has a great influence. This quantity, this particular parameter texture has a great influence on mechanical, electrical, magnetic, optical properties of our materials. Texture is usually quantified by a term called the orientation distribution function, or ODF. It can be loosely defined as like a volume fraction of materials, volume fraction of grains having preferred orientation or certain orientation. This orientation distribution function or texture is graphically represented using a graph called pole figure. The theory of pole figure we will discuss in the later slides. The pole figure shows pole figure is a two-dimensional stereographic plot that shows how a particular crystallographic direction is distributed relative to the sample surface. That means in pole figure, we plot how a particular crystallographic orientation is distributed with reference to the sample surface or scattering vector. With reference to the sample surface, how a particular crystallographic orientation or how a family of crystallographic orientation is distributed. The theory we will discuss later. So how can we determine preferred orientation in a sample? There are various methods by which we can determine the preferred orientation in a sample. One simplest method is to compare the relative intensity of a particular peak obtained from theta to theta scan with the relative intensity of the same sample which does not have a preferred orientation. Yet another method is to use a rocking curve analysis. The width of the rocking curve will give the texture parameter. Another method is to perform a pole figure analysis to determine the presence of grains having preferred orientation. And another method is to use multiple pole figures to determine the orientation distribution function. The orientation distribution function is actually a mathematical term, mathematical function. It's three-dimensional mathematical function, which can be obtained from the reciprocal space mapping. Another method is to use reciprocal space mapping, through which we can determine the strain in the thin film, interfacial defects, doping, tilting, twinning in the crystallites that can be determined easily using reciprocal space mapping. So what are the advantages of using pole figure among these methods? In the case of pole figure, we can directly determine the texture orientation, and we can also quantify. If we want, we can also quantify them. There are several software, simulation software available there. And in the case of pole figure, the crystallographic orientation between the film and the substrate. If we are studying a multi-layered structure, we can also study the orientation between the films, between the film or the substrate. And even we can determine the twinning or tilting in the thin films that we can easily determine in the pole figure analysis. So how do pole figure measurements are performed? In the case of conventional theta to theta geometry, reflections only from a subset of planes are taken. That means, as we have discussed, only from theta to theta geometry. In the case of theta to theta geometry, reflections from those planes which are normal or which are parallel to the sample surface is only taken. That is, we are taking reflections only from a subset of planes available. But in the case of to understand the orientation distribution of the sample, reflections of all grains in the sample has to be evaluated. This is performed by pole figure. That is scanning the reflections under various orientation. That is what we do is we take the measurements. We measure the Bragg intensity under various rotation angles in psi and phi. Psi, as we have already discussed, psi is a tilting angle. It is the angle between the scattering vector and the surface normal. By tilting the sample and rotating the sample, for a particular tilt, we will rotate the sample from 0 to 360 degree, and we will measure the Bragg intensity of the peak. This is how we do the pole figure analysis. For each tilt, we will rotate the sample from 0 to 360 degree. Then the tilt will be slightly varied. Then again do the phi scan. Then again we tilt the sample. Then again do the phi scan. That means we will again rotate, and we will continuously measure the Bragg intensity of the Bragg reflections. As you can see, this is the phi angle and this is the tilt angle. For each tilt, we will be rotating the sample from 0 to 360 degree. Psi, we will be tilting from 0 to 90 degree. In most cases, theoretically, it is possible to vary 0 to 90 degree. But in most of the instruments, HRXRD instruments, we can go from 0 to 80 or 85 only. So by tilting, for each tilt, we will rotate the sample and we will collect the Bragg reflections. This is the instrumentation setup needed to for pole figure. In the case of pole figure, we for a particular tilt angle, we will rotate the sample and we will measure the intensity of the Bragg reflections. As we discussed here, this is a sample. As you can see, this is a sample. Here, for each tilt value, for each tilt angle psi, we will rotate the sample from 0 to 360 degree, and the reflections from the Bragg reflections are measured. As you can see, these poles, these reflection will exist on the surface of a hemisphere. That means the measured poles will exist on the surface of a hemisphere. These reflections exist on the surface of a hemisphere. In order to make it for publication, we have to project these poles into a two-dimensional plane. An example is shown here. This is a pole figure of basic crystallographic axis 100, 110, 111 plane for a 100 oriented cubic cluster. That means our sample, this is our sample. Sample here, the sample is 100 directed. That is sample norm. This is the direction of 100 direction. So our sample is 100 oriented, and we are taking the pole figure corresponding to 100, 111, and 110. The measured pole figures will exist on this surface of the hemisphere. For example, these orange dots denote the pole figure corresponding to 111, and this brown dots denote the pole figure corresponding to 110, and this black spots corresponds to the pole figure for 100 orientation. As you can see, all these measured poles will exist on the surface of a hemisphere. So you will have to, we cannot do a 3D picture in our, we cannot insert a 3D picture into our publication. So we have to project these poles into a two-dimensional plane. It is a traditional problem in cartography. There are different methods available to project these poles on the surface of a hemisphere to a two-dimensional plane. Two of the methods are Wolf projection and Schmidt projection. Wolf projection, also called a stereographic projection or equal angle projection. Schmidt projection is called a equal area projection. In the case of Wolf projection or Schmidt projection, what we do is that we project a pole into an equatorial plane. This is the equatorial plane. We project this pole into equatorial plane using different methods. In the case of Schmidt projection, here this is the pole, and we project this to a two-dimensional plane. A top view of this two-dimensional plane or equatorial plane is shown in the figure. This top view or this equatorial plane is called a pole figure graph. So whatever method we are using, what we do is to project a pole into into the equatorial plane or a two-dimensional plane, and that two-dimensional plane is called a pole figure. For example, here we are considering the pole figure corresponding to basic crystallographic axis, that is 100, 111, 110 planes for a 100 oriented cubic crystal. That means here this is our sample. This is 100 oriented. That is this normal direction. Sample normal is 100. And how we can do how we do this pole figure? We tilt the sample in the psi direction and rotate the sample in the phi direction from 0 to 360 degree. So how we can do the how this 100 pole figure is obtained, that we will discuss. As you can see, I have a Rubik's cube. Here, this is the cubic structure with the 100 orientation. Unit cell with the 100 orientation. This is the 100 orientation. I think you can see my video. This is the 100 orientation. Without any tilting or rotation, I can see 100 plane. If X-ray came to this plane and diffract, we will get a diffraction peak without any tilting or rotation. That is, at a psi is equal to 0 and phi is equal to 0, we will be having a particular pole. That is shown in this figure. Now, to obtain another 100 plane, how much degree we have to tilt the sample? We have to tilt the sample to 90 degree. So between 0 and 90 degree, there is between 0 and 90 degree of tilting, there is no another 001 oriented family of planes. By tilting the sample to another 90 degree, we will get another 100 family member. So we will get a one pole at this angle, at this particular angle corresponding to psi is equal to 90 degree. By rotating the sample in the phi direction, that is azimuthal rotation we are conducting, by rotating the sample to another 90 degree, we will get another family member that corresponding to yet another pole corresponding to 180 degree of phi. By rotating in the phi direction by another 90 degree, we will obtain another family member, that is 0 minus 1 0. Another pole we will obtain. Then by rotating again by 90 degree, we will obtain another pole at 270 degree corresponding to 100 direction. This is how pole figure analysis is done. So for each psi value, we will rotate the sample from 0 to 360 degree. Another example for 111 plane. From a cubic crystal which have 100 plane, to obtain a 111 plane, first we have to tilt the sample, rotate the sample from 0 to 45 degree, and then tilt the sample to 57.4 degree. In that case, our 111 plane will be now normal to the scattering vector, will be normal to the sample surface. 111 plane will be normal. So we will get a one pole corresponding to 111 family. Then by rotating 90 degree, we will obtain another pole. Again, rotation by 90 degree, we will obtain three another poles for 111 plane. Here, psi angle is in the radial direction and phi azimuth angle is in this direction. This is how this is what we have explained for the case of 111 pole figure for a 001 oriented crystal. We will obtain the 111 peak by rotating the sample, by tilting the sample by 57.4. We will get one family of 111 plane. We will get corresponding to that, we will get a Bragg reflection. We will get a peak, high index peak at this angle, tilt angle. Then by rotating 90 degree in the phi direction, in the anti-clockwise direction, we will get another 111 family member at a 135 degree. Then again by rotating 90 degree, we will get another family member 1 bar 1 1. We will get another intense peak at a 225 degree. And again by rotating 90 degree, we will get another peak. So the sample rotates along the phi direction and records a Bragg reflection. We can observe sharp intense peak at regular intervals. Here in this case, it is around 90 degree corresponding to 111 family members with a tilt angle of 54.7 degree. All these directions, that is 111 minus 111 or bar 1 bar 1 1, all these directions are symmetry equivalent in a cubic system and lie at the same tilt angle of 57.4 degree from the sample normal. The angle between these planes can be easily determined using our basic crystallographic equation, and that is given by cos theta is equal to h1 h2 plus k1 k2 and so on. If we substitute the 110 and 111 values here, we will get the angle of 57.4. And the schematic representation of a 110 pole figure for a 1001 oriented cubic structure is shown in the figure. And the basic pole figure corresponding to 111 oriented planes. Earlier we have seen 100 oriented planes, basic pole figure corresponding to basic crystallographic axis of 100 oriented planes. Here in this case, the sample normal is 111, and then the pole figure will be like this. I'm not going to explain in detail here. Only thing you should note here the second figure that we need for our later discussions. In the case of 111 oriented thin film, the 111 pole figure will be like this. We will get a pole figures at a size equal to 90 degree, 110 degree, 330 degree for a tilt angle of 0 and 70.5 degree. Now, this is the stereographic projection for basic crystallographic axis in for a system with a 001 orientation. You can see 001 orientation at the center. This is the basic stereographic projection for a cubic system with a 011 orientation. This is a stereographic projection of pole figure for basic crystallographic axis in the case of 111 oriented crystal. These figures you can see in basic some basic books like Kuliti, you can see. Now we are going to discuss how we can use pole figure to determine the orientation distribution in our own sample. Figure shows a XRD spectrum of bismuth zinc neobeta thin films deposited on Al2O3 substrate with a zinc oxide buffer layer. As you can see, this is the bismuth zinc neobeta thin film directly deposited on Al2O3. We could see peaks corresponding to BZN 222 and 00 peaks. That means the BZN thin film here is a polycrystalline growth. We obtained a polycrystalline growth here when BZN directly deposited on Al2O3. Whereas when BZN deposited on zinc oxide buffer layer, that is when BZN deposited with the help of a zinc oxide buffer layer, we could only see reflection from BZN 222 rather than other than that of zinc oxide buffer layer and the substrate peak. That means this sharp intense peaks tells that our films are oriented along the highly oriented along the 222 direction. It should be noted that in the y-axis the intensity is given in the log axis. It is of the order of 10⁶ counts per second is in the y-axis. So the high intense peaks of BZN thin films shows the epitaxial nature of the thin films. The epitaxial growth of BZN thin films were also confirmed using high resolution transmission electron microscopy. This is a cross-sectional image of BZN thin film deposited on Al2O3 with a zinc oxide buffer layer. The Fourier transform image of the black box area shown in the first figure is given in the second figure, and SAAD pattern is also given. The sharp intense spots and sharp interfaces again confirms the epitaxial nature of the thin films. So this is the pole figure corresponding to that film. As you can see here in the pole figure, we got one spot at the center for the BZN thin films with the 222 orientation. We can see one pole at the center, and you could see three another poles at a tilt angle of psi is equal to 70.5 and with a angular separation of about 120 degree. The angular separation is here. Here the angular separation is about 120 degree. Whereas in the case of epitaxial thin films, or when we grow BZN thin film with on the zinc oxide buffer layer, you could see that there is one peak at the center. In addition to that, there are 6 poles. We could see 6 poles. In addition to the previous 3 poles, we could see another set of 3 peaks at the same size equal to 75 degree, but an angular separation of now the angular separation is about 60 degree. So what does this signify? From where does these additional peaks came from? And what are the structural informations can we get from these additional poles? These additional poles can give some additional information regarding the structural orientation of BZ and thin film on zinc oxide buffer layer. As you can see, in the case of 111 oriented, as we have discussed earlier, for the 111 oriented film, the pole figure corresponding to 111 will be giving only 3 poles at a psi is equal to 70 degree with the 120 degree as in the first figure. We are observing. So there is an additional 2 peaks. These 2 peaks, the additional set of peaks can give additional information regarding the structural orientation. These set of peaks come from the thinning of BZ thin film on the zinc oxide buffer layer. This is a proposed model for epitaxial relationship between BZ and zinc oxide. As you can see, in the case of BZ, which have 2-2 orientation or 1-1-1 orientation, bismuth is situated at the corners of the 1-1-1 peak. It can be oriented above the hexagonally placed oxygen site in 2 different ways. Either this bismuth can orient along this O dash sites, these O dash sites, or they can be oriented along this O double dash sites. That is, these O double dash sites is 60 degree twin direction. So our 111 peak can have 2 different orientations here. Either these 111 oriented peak came to the O dash sites in this direction, or O double dash sites which are 60 degree tilted. That means here the bismuth cations can have 2 possible stacking sites separated by 60 degree. This 2 equally probable stacking sites for bismuth, that is O dash and represented by O dash and O double dash, give rise to twinning of the BZ and 222 peaks. That means BZ and 222 planes are twinned, that is rotated along the sample surface. Equal intensity of all the peaks. These peaks corresponding to the bismuth atoms, where the bismuth atoms oriented along O dash sides, and these set of poles corresponding to BZ and 222 planes, which are oriented 60 degree twinned directions. Equal intensity of all the peaks. So you can see all these 6 poles have equal intensity. Equal intensity of all the peaks says that the 2 orientations, both O dash and O double dash orientations, are equally probable. These type of informations, that is twinning in the crystallites, you will not get this type of information from ordinary XRD or other characterization techniques. You can only get it from pole figure analysis. XRD 5 scan is given. Hello? Hello, Sanal. Shall I continue or can I stop here? Hello?
Yes, doctor. It's been an hour. If you conclude.
Okay. Here the reciprocal space mapping. I'm not going to discuss reciprocal space mapping in detail. We know that what is the reciprocal lattice vector and how we configure, how we determine the reciprocal lattice points or reciprocal lattice spaces. In the case of, I'm concluding my presentation. In this case, usually we represent the reciprocal lattice points using a sharp, intense, well-defined circles. Whereas if there are twinning in the crystallites or strain in the crystallites or other composition gradient in thin films, this shape of the reciprocal lattice point will change. Shape, size, or orientation of the reciprocal lattice will change. From that, we can infer how much strain is there in the film. Here, look at this figure. In the case of a composition gradient, the reciprocal lattice points will be elongated like this. By conducting a reciprocal space mapping, we can, if the reciprocal lattice points are elongated in this way, we can conclude that there is a compositional gradient. If the reciprocal lattice points are shifted like this, we can conclude that there is a strain gradient in the thin films. If the reciprocal lattice points are elongated perpendicular to this perpendicular to the scattering vector, there is a presence of defects in the thin films. So there are many different ways by which we can quantify strain or compositional gradient, or there is a tilt or defect in the thin films by various XRD characterization tools. Here in our sample itself, you can see reciprocal space mapping of BST thin film at the center, and zinc oxide buffer layer you could see here, and the reciprocal lattice point corresponding to Al2O3 substrate you could see here. Here it indicates all the peaks are at the same scattering vector direction. That indicates the same in-plane lattice parameter. That means the films are pseudomorphic, film grown pseudomorphically, and the sharp indents peaks signify high crystalline quality of the thin films. It all, since the elongation of the reciprocal lattice point is along on the omega direction, it confirms uniform despacing over the sample. So summarizing my presentation, what can be learned from XRD techniques? In the case of normal XRD theta to theta scan, you could do phase identification, which will give the lattice parameters. From that, we can calculate crystal structures, lattice parameters. Using Rietveld analysis, you can determine the crystal structure also. Using GID, you could do surface phase analysis. It is usually used for polycrystalline thin films to identify phase identification, crystalline size, or crystallinity. Using pole figure analysis, you could measure texture or preferred orientation into the sample, or symmetry or epitaxial nature in the thin film can be confirmed using pole figure analysis. In the case by using reciprocal space mapping, strain versus relaxation means strain in the thin films, lattice mismatch in the thin films, etc. can also be done in the case of reciprocal space mapping. In addition to that, we can also do in situ capabilities like evaluate the properties or evaluate the X-ray diffraction as a function of time, temperature, and the gas environments can be done. So X-ray diffraction technique is a critical plays a critical role in characterization of thin films and nanostructured materials. So thank you for inviting me. Thank you ECS UNL Student Chapter and the UANL. Also a special thanks to Dr. Sanal for inviting me to this webinar. Thank you.
Thank you, Doctor. We have a few questions. What pattern is plotted between intensity and 2 theta specifically? Additionally, why we have 2 theta in XRD graph instead of theta?
Excuse me, could you please repeat?
What pattern is plotted between intensity and 2 theta specifically? Additionally, why we have 2 theta in XRD graph instead of theta?
Oh, okay. See, if you go into the Here, in this case, the sample direction, normal direction, the detector angle, what we actually measure is the detector angle. The detector angle is between the incident beam and the detector is angle 2 theta. This is the angle we are with which the detector is moving. That's why we take 2 theta along the x-axis, not theta. I think that answers your question, right?
Yes, thank you. Next question. What is the difference between XRD and high resolution XRD?
Oh, that we already have discussed. In the case of XRD, we can only do some limited scans. Like we can only observe planes that are grown parallel to the sample surface. Whereas in the case of HRXRD, it has high resolution. As I said, it can have a resolution beyond 0.001. In most of the cases, it will be around 0.001 degree resolution. And in the case of XRD, we can all do not only the theta symbol Bragg-Brentano geometry, we could do 2 theta omega scans, omega scan, reciprocal space mapping, pole figure analysis, and all these things we can do in HRXRD, high resolution XRD. High resolution itself means the angular resolution. The angular resolution is very high. In the case of a normal XRD, it is around 0.1, or usually it will be around 0.5 degree. In most of the HRXRD, the angular resolution will be around 0.001 degree. That the name suggests high resolution XRD.
Okay, in the composite XRD, like two metals, is it possible two metal XRD peaks in the same position?
In the case of composite,
Yes.
you are saying metal composite thin films, or in case of composite thin films, you could do the XRD measurements. You could do normal XRD, or what you have to do is do the glancing angle XRD. In the case of glancing angle XRD, when we do glancing angle XRD, even if the composites or unit cells are tilted to the sample surface, you could measure that also. You could see the peaks corresponding to the tilted orientations also. So it is possible.
Last question. How reflection is handled or taken out of the graph?
Hello, excuse me.
How
Can you please repeat my question?
reflection is handled or taken out of the graph?
How deflection?
Yes, how reflection is handled or taken out of the graph.
You mean how we analyze the thin films? The intensity, the reflection intensity, intensity of the peaks are measured using a detector. And from the peak intensity itself, you can say that this much planes are aligned, or you can say that this much proportion of planes are oriented along a particular direction. That's the intensity significance of the intensity.
Okay, thank you, doctor. I think is all the questions.
Okay, so thank you very
Okay,
much, Dr.
thank you.
Krishnaprasad, and thanks to everyone who joined us today. On behalf of the UANL ECS Student Chapter, I would like to extend our sincere gratitude to our speaker for sharing such an insightful and engaging presentation. Though we are limited by our time, I would also like to thank Dr. Teresa de Jesus for the warm introduction and for guiding today's session. A heartfelt thank you goes out to all participants for making this initiative truly impactful. Finally, special thanks to the organizing team behind the scenes. We look forward to welcoming you all again for our upcoming sessions. Until then, please stay connected, stay curious, and stay inspired. Please do check out the feedback form before you exit the session. Thank you very much and have a wonderful day.